Okay, hello, this is Dr. Muhammad, and this is another video on the dynamics of structures. And today I'm going to talk about the damped free vibration response of single degree of freedom system. So in this regard, we're going to start directly on the equation of motion. So let's start with the equation of motion. And for the equation of motion here, we are going to add the term for damping. So it is going to be mu double dot plus cu dot plus ku equal to 0. And this is going to be our main equation. Let's give it like a number here and say that it is number 1, equation number 1. The point is, we are going to deal with our system as if damping is there. So this term, which is cu dot, it was not there before in the previous undamped system, but here it is existent. This means that the solution, the solution of this equation, okay, the solution for this equation is going to be solved also mathematically, and if we are going to solve it from the mathematical point of view, we're going to find that u of t, okay, which is the displacement at any time, can be described as a constant d times e to the power p times t, where these are constants here. So this is like constant, and this b sorry, it is another constant here. So this is considered to be the solution of equation of motion. This is the solution of equation of motion. You are going to find a new term that is going to be added here, which is e to the power pt. I mean that we didn't see this exponential function before in the undamped system, right? From here we can say, let's have the first derivative and the second derivative of our system, okay, or the solution, because we need to like use it in our main equation, because here this is the equation of motion. So we know now u, which is dE to the power pt, but we want to get u dot and u double dot. So we're going to differentiate here easily, and we are going to find that our system is going to be differentiated, this is the equation after being, or the first derivative of u of t, which is the velocity here, and then u double dot of t, it is going to be d p squared times e to the power p of t. Remember that the derivative of d by dx for e to the power t, it is going to give us e to the power t, for example, times dt to x. So remember this well. I'm going to write it here. D by dx for e to the power t, it equals to e to the power t, then dt dx. Okay, so now we have the three components here, that is, we can substitute in our main equation, right? So now by substitution in 1, which is equation number 1, we're going to find that our system is going to be m d p squared plus c d p plus k d times e to the power pt. If you substitute with these three equations here into the main equation, equation number 1, you are going to find that we will get this value. And we are going to like take d as a common factor here, and we can put it like this: m p squared plus c p plus k times d e to the power t. So like we have two terms here, right? So this is the first term and this is the second term. And we are going to equate it with 0 at the end, because the right hand side of this equation is 0. So there is one term need to be equal to 0 and the other will not be. So actually this term is what? It is changing with time. This is, it changes, okay? It changes with time, right? So definitely this means, if this is like 0, this means that there is no motion here, there is no response at all. But this term should be 0. This term should be 0, right? So this means that we are going to equate this term, okay, to 0, and then let us see what will, what we are going to obtain after that. Okay, so now let's go to this. Okay, that is equating mp squared plus cp plus k equal to 0, right? It seems to be like quadratic equation, and we have like, this is the term of a, and here we can say this is c, and this is like, this is, sorry, b, and this is c. So it's a quadratic equation, we equate it with 0. In order to obtain the roots, we can say that we have two roots here, like p1 and p2, and it equals 2 minus c over 2m plus or minus the radical of c over 2m squared, right? Minus k over m. This is what we are going to have here. Okay, so this is the solution of this quadratic equation, and these are the roots. The general solution, so we can write something here that our mathematicians, they said that the general solution of equation 1 is given by the superposition, means that adding, okay, the superposition of the two possible solutions, right? What is the meaning of the two possible solutions? We have one P1 and we have another root which is P2. So this means that our equation, okay, from here we have like P1 and P2. Right? So this means that our equation is going to be, which is u of t equals to d1 times e p1t plus d2 times e p2t, because as I said we have like p1 and p2. So let's assume that this is, for example, equation 2 here, okay, important, and let's give this equation also, let's put it like 3 here, okay. So we have, from this, we have, from where we got this equation, this is the solution, the first solution here. Let's go back. Here, this is the solution, u of t, right? We mentioned about this. So this is our solution. So we have d and we have p. So p is 1, p1, then we have de or d1e p1t, and another solution which is d2e p2t. So we are going to have the two solution, which is, I put in this note, the general solution of this equation here. It is going to be the superposition is given by the superposition of the two possible solutions, P1 and P2, which is already, we're going to obtain them from equation 3. Okay, so what is D1 and D2? So this is D1 here, and we have like D2 here. They are what? Yes, exactly. They are constants. So we can say that D1 and D2, they are constants of the integration to be determined from the initial conditions. Okay, so these are like the constants of the integration to be determined from the initial conditions, D1 and D2. D1 and D2. Okay, I'm going to write a hint here. Maybe it is suitable to mention about it. There's an important hint that we can mention about it. The final form of equation 2, let's put it, this is the green color, the final form of equation 2 is dependent on the sign of the term under the radical, is dependent on the sign of the term under the radical, right? Which is what here in our case? Exactly, it is c over 2m to the power 2 minus k over m, right? So this means that we have like 3 different cases. Here we are going to have 3 different cases, right? The first case, when that we are dealing with 0, okay, if the radical under the radical equals 0, and this is what we call it like the case of critically damped, critically damped system, and this is, we are going to give it like case number 1. There is another case which this value under the radical is going to be negative. This means we are going to call it underdamped system. We call it underdamped, okay, system. And this is, we are going to give it as case number 2. And then the last case is going to be the case where that we have positive value under the radical, and this is what we call it the overdamped system. This is overdamped system, and we are going to give it as case, or title like case 3. So we have different cases based on the value of the term under the radical. So if it is going to be 0, means that our system is going to be given the term that is critically damped. If it's negative, then it is underdamped system, and if it's positive, then it is going to be like overdamped system. And we are going to study our these systems in detail. Okay, and let's actually, most of the structures fall into the underdamped system. So here we can say that most of structures fall into this category. Okay, this category, which is the underdamped system. Most of our structures, they are underdamped. Okay, even that we have like critically damped, we are going to talk about them in a minute, but in general, our structure systems, they are falling into the underdamped system, Okay, now we have these 3 cases. Let's study each case in detail. In today's video, I'm going to study only about case 1, which is 0, which is the critical or critically damped system. Okay. Now, let's put it in more concise form and say that in our case, we have, let's assume that this is case number 1. Maybe next lecture I'm going to talk about other cases. This is going to be, as I said, when the radical, which is c over 2m to the power 2 minus k over m is going to be equal to 0, right? So this is the case if this value under the radical is going to be 0. We are going to give here subscript for this CR, we call it CR, which means critical, okay, only to differentiate it from other types of damping coefficient, okay, to differentiate it from the other damping coefficient. So this means that we can say that C over CR equal to over 2m, it should equal to the square root of k over m, right? We're going to equate both of them. So it is, yes, that's right. So we have this C over CR over 2m should equal to the square root of k over m. And from here we can say that CR equals to 2 square root of k times m, right? Based on this, we can say that this CCR equals to 2 times, like if I'm going to say like k over m times m squared, okay? This is the case. I didn't do anything, just I added m in the numerator and denominator. And then when you look to this, you're going to find, well, this is going to give us 2 times k over m under the radical, it is omega, times m squared under the radical, then go outside is going to be m here, right? So C critical is going to be 2 omega m, okay? And this is what we have explained about omega last time. So this means that our CR, the critical damping coefficient, is going to equal 2 omega m, and this is going to equal to 2 times k over omega, right? Because actually we know that k equals to omega squared m, right? So in this case, 2 omega m equals to 2 k over omega. And this is what we call it the critical damping coefficient. The critical damping, damping coefficient. Critical damping coefficient. Then we're going to substitute. Now we obtained our critical damping coefficient here. This is the 1. Now substitute in equation number 3. Let's have a look at equation number 3 again. So this is equation number 3 here. P1 and P2, we have like two different roots, but the point is, in this case, we are going to have the terms under the radical is going to be 0, so we do not have 2 roots here, it's going to be 1 only. Plus and minus are not going to be there anymore because this is going to be 0, right? Okay, so in this case, we are going to have that only 1 root, it is going to be 2 minus omega m over 2m, okay? Plus or minus the square root of whatever here is going to be 0, right? In this case, we are going to have that P, m cancels out with this 2 with 2. This means that P is going to be minus omega. This is going to be the only one solution of the equation. This is the only one solution of equation number 3. Okay, this is the only one equation. Okay, So the point here is, what is the meaning of C critical? What is the meaning of C critical? What is the meaning of this equation here? So we can write down this and put it here. Can write down this. Okay. And we say that this means, what is the meaning of critical? Okay, the word critical here and in this equation. This means that if the motion starts from U node, starts from initial condition with U node displacement, okay, and velocity V node, so we have U node and V node, means that there are some initial conditions here. The mass, okay, the mass of this system will return to rest condition, without oscillation. What is the meaning of this? This is very important and powerful hint regarding understanding the critical damping. That in this equation, simply what we are having here in this equation is telling us that if we started our system, or if we initiate the system with U node and V node initial velocity and displacement, the system is going to be under motion. The mass will return to its rest condition without oscillation. So this mass is going to go here and then go back without any kind of oscillation. Okay? That's the meaning. And that's the meaning here. Okay? This is the meaning. But let's define C critical. Let's define C critical. Okay? Now we can understand that we have U node and V node. It is going to take like play some part here in our equation. In the coming part, you're going to find U node and V node. However, if you look to the previous videos for the undamped, we said that there is no initial condition is going to be contributing. There is no initial condition is going to be contributing to the equation. U node and V node is not existent there. So based on this, let's define. Okay, make definition of C critical. What is the definition of it? Okay, we can say that it is the smallest value of C, which is the critical or the damping coefficient that inhibits or prevents oscillation completely. Okay, it is, we can call it like this, it is the dividing line between oscillatory and non-oscillatory there is O here, okay, motion. Okay, so this is the definition of it. What is the meaning of this? Again, let's go and understand more about it. It's the smallest. This means that we're talking about the smallest possible value of the damping coefficient. the damping coefficient. What is the smallest value, or not? We're interested in the smallest value. The smallest value of the damping coefficient that inhibits, that prevents oscillation. So our system is not going to oscillate, okay, completely. So our system is going to start, okay, to go, and then at this position it will return back without oscillation. So it will not go in this direction again and go back again. No, it will not do like this. It will go in one direction and then go back to the rest condition. It is the dividing line between oscillatory and non-oscillatory motion. Okay, it is the dividing line between the oscillatory and non-oscillatory motion. Okay, now let's go and make and obtain the solution of the differential equation 2. Now remember that we have, this is our main, the general, okay, the solution. The two, or the possible solution for our system is here. So let's try to solve it. Let's try to solve it. Okay? Solve this equation. Okay. So we're going to say the solution of the differential equation number 2. So the solution of the differential equation 2 is going to be, we call this independent solutions. Okay, we have like two independent solutions. Our mathematician friends, they told us that we have two independent solutions. U1 of t, which is going to equal d1 e to minus omega t, and we have another solution which is u of t equals to d2 times t times u1 of t, which means that d2 times t times e to minus omega t. Okay? Because we have here like two solutions. Again, we are talking about our main equation that we have here, okay, which is this d1e to 1 p1t plus d2e raised to the power p2t. So this, the solution here, okay, of this equation is going to be one of these two possible solutions. You are going to ask me from where we got this. As I said, that mathematicians told us that if you want to be sure, you can go back. You can go back to the original equation, because our original equation is u of t equals to d1 e to p1t plus d2 e to p2t, right? This is our original equation. This is equation 2 if you go back. So if you try to substitute with this first solution here, it will work with you. And if you substitute with another equation, which is d2 times t times u1 of t, which is this solution also here, which gives us d2t times e to minus omega t. Actually, d1 times d2, it will be also another, that the same constant or another constant that is, doesn't matter whether it's d2 or d3 or whatever, it's a constant. Okay? So this means that it will work and it will satisfy this equation. These two, okay, equations, or these two solutions are going to satisfy this equation. Okay. Based on that, we are going to say that the general solution is going to be, for our case, it is going to be u of t equal to d1 plus d2 t times e to minus omega t. The general solution is going to be the summation of both. Summation of both. We have d1 e to minus omega t, which is this one, and we have the other one, the other solution, which is Okay, d2t times e to minus omega t, right? Then the general solution is going to be this solution. Let's go back again with the red color. Introducing the initial condition to get the final equation of motion, we're going to use now the initial conditions, which is u node and v node. Okay, use the initial conditions to obtain or to get the final equation of motion. We want to get the equation of motion now, EOM. Okay, so we're going to say this requires to calculate u dot of t. Okay, from here u dot of t, it is going to equal to minus omega d1 plus 1 minus omega t times d2 times e to minus omega t. From where this, you can use it by the chain rule. We're going to find that you have two functions here. And we have the independent variable t is in two different functions, d2 t times the exponential function here. By the chain rule and rearrangement, you're going to obtain this equation. Okay? Then add the initial condition, means that at t equal to 0, what will happen? Let's go to the next y page to make it. So we say that at t equal to 0, what will happen? In this case, u is going to be u node, which is going to be d1 directly. Let's go back here. U is going to be u node. So u1 is going to be e to minus omega t is 0. So we are going to have u is going to be d1, right? And after that, u dot is going to equal to v node, and it is going to be equal to minus omega d1 plus d2, right? If you are going to substitute here also, u dot, this is u dot here, so if you substitute, you're going to find t here is 0, so 1 minus 0, it is 1 d2, and e to minus omega t, it is going to be 1, and omega d, so it is going to give us minus omega d1 plus d2, right? Okay, so this means that from here we can say that d1, the constant, is going to be u node, and d2, the other constant, is going to equal v node plus omega u node. Okay, so this is the case here for us. Now let's substitute in our main equation, which is the last equation that we have obtained. So it is u of t equals 2. Now let's open this square parenthesis. So we have u node plus v node, another like curved one here, plus omega times u node. This is times, huh? So times t, and then close this parenthesis, e to minus omega t. This gives us at the end, that is u node 1 plus omega t plus v node t, and close it, and then here e to minus omega t, right? This is what we're going to obtain after the substitution. Okay, we're going here, this is the substitution, this equation, okay, this is the substitution in the general solution. So we are having the general solution. Okay? Okay, in this case, we can say the critically damped equation, the critically damped equation of motion, the critically damped equation of motion is going to be like this. U of t equals to U naught times 1 plus omega t plus V naught t, close it, and then E outside E minus omega t. This is going to be our general equation of motion for the critically damped system. For the critically damped system. Look to this term. Look to this term. There is something interesting here, okay, which is the exponential term. This exponential term, mathematically, we're going to call it the decay term. Decay term. What is the meaning of it? This term is responsible for decaying the response. So it is going to make the total, or the output of this equation is going to be decaying with time, because we have t in the power of this exponential function. When we are going to draw it, we're going to find, if we're going to draw, we're going to find something like this, which is a relation between u of t in the vertical axis, and we are going to have t in the horizontal axis, and we are going to find that our equation is going to be having this form, okay, where that here in the beginning, okay, here this distance, vertical distance, is going to be the original at t equal to 0, right? It is going to be u naught. This is the case of the initial condition. This is the initial condition. This means that we are going to have u naught here, and the slope here is going to give us what exactly? It is v naught. Okay, u naught and v naught. Okay, and then the equation is telling us that the equation may raise up like this. But after that, what will happen? It is decaying like this, going like this, decaying. What is the reason for this decaying? It is the term e to minus omega t. It is the main reason for this kind of decaying of it. And take care here at the end, we didn't go beyond this horizontal axis. Remember that we prevented oscillation around it. So, yes, we cannot go to the lower half here. No, it is only the upper half, and the system is going, as I said before, if you are going to make it like this, this is our system, and the system, if it moves, then it's going to move in this direction, reach the maximum, and then go back here to the rest condition. It will not go again here. It will not go to the left part. Okay, so now let's put and write some notes about this, what we have mentioned here. So let's write some important notes about what we have understood. So number one, and the most important for non-critically damped, it is no oscillation about the zero deflection position. No oscillation, okay, about the zero deflection position. Okay, you understand it here? As I said, no oscillation here. No oscillation means that we didn't go in this direction, for example. Okay, this is number one. And number two, the exponential decay term, okay, this term, which is the term, we call it e minus omega t, this term, is responsible to return the motion to the rest condition, to the rest condition. That's very important. So if we go back here, you're going to find that here, this is due to the e to minus omega t, okay? Due to the decay term, which is returning the motion to its zero condition again. Okay. And number 3, if we're going to define the critically damped condition in general, so it is the definition, if we say that it is the definition, okay, of the critically damped condition, we can say it is the smallest amount of damping. This is the definition, you need to remember it. The smallest amount of damping for which no oscillation occurs in the free response, and the free response. Okay. Okay. And the last thing is going to be some examples for our critically damped system. There are different examples actually. I'm going to start with the like instruments such as speedometers are critically damped. So you can find in your car, for example, you're going to find something like this, the speedometers. These speedometers are critically damped, so when a car accelerates, the speedometer quickly changes and it doesn't oscillate and confuse the driver. Yes, this line is not going, it goes here and then it goes back directly. It is not going to like going here and then going here and then going here. No, we want it to be only to reach to the point and that's it, and then go back again. So it will, in order not to confuse the driver. Another example that is common example also is the gun. So for the gun, it is made critically damped so that it returns to the neutral position in the shortest time between firing. Okay, so this another example, that is, you can write it like this. It is made critically damped so that it returns, okay, to neutral position in the shortest time. So if we have like a in firing, there is something here. This, like whenever the firing is being or the shooting, then this goes back after firing. It goes back to the original condition, so that in the shortest time between firing, so that you can use the gun like easily without waiting. Another thing is the scale, which is the scale measure. The scale measuring, you can find this scale measuring in any place, which is the scale measuring the dead weight. Okay, so it is considered to be another example for critical damping. Like these are the most common 3 critical damping examples. Okay. By the end of this, I came to the last slide of this presentation. I hope that you have understood this undamped system, and I hope that in the next videos you are going to understand more about the different systems and the different cases where that we have underdamped system and we have the overdamped system, and we are going to explain about them in the next videos. Thank you, and see you in the next time.